Welcome everyone to the 10th episode of BeyondPhrenology, and we are delighted to have with us today Brandon Thomas. Brandon is a assistant professor of psychology at University of Wisconsin-Whitewater. He did his Ph.D. at University of Cincinnati and followed by a postdoc at University of Utah. And Brandon comes from the ecological tradition. I can say he's a staunch ecological theorist. And I met Brandon for the first time in 2015 at the International Society for Perception Action in Minnesota. And I think we struck chords there. And since then, we have been in touch, and I've been following Brandon's work, and he has also been contributing towards my projects. So, Brandon, welcome to the show.
Great to be on it. Thanks for having me.
So, Brandon, for the viewers, let's start with eco-psych. What exactly is this ecological psychology? What kind of beast is that?
Yeah, so the question is, what is ecological psychology?
Yeah.
Yeah, that's a interesting question. So, the origins of ecological psychology are, of course, James Gibson's and Eleanor Gibson's work in the through like 1940s or 50s through the 1970s, and then of course Eleanor kept going for a long time after that too. But the ecological perspective is, I would say, it started off as a new explanation for phenomena that's the approach, or the contemporary standard approach at the time couldn't explain. So it sort of stems from addressing some of those anomalies, and I think one of the biggest ones is just the relationship between the individual and the environment. So rather than defining them as separate, but interacting with each other, they're defined by Gibson and other, ecological psychologists who've followed them both as being a singular entity, and the idea that you can't understand how an organism thinks, behaves, or perceives the environment in any way without taking into account its relationship within its ecological niche, excuse me. And I'd say that is the general background of the concept, but of course, there's a lot more components to it. So you can get into the redefinition of information and so forth, and the other components that have followed in Gibson's and others' work.
I see. So how is that different than traditional psychological theories, more cognitivist and more representationalist?
Yeah, I think what's happened in ever since the 1600s or so is that we all started to define the mind as this entity that exists outside of reality, what we'd otherwise describe as reality. And a lot of people were responsible for this. Obviously, think about Descartes and his brand of dualism as one of the starting points of this line of thinking. But there's all sorts of other contributors to it, some of them scientists even. So it was the case as well that Galileo was someone who didn't found that he couldn't trust his own necessarily astronomical observations and those of others to be perfect or precise. And the idea is that there's some sort of subjective realm that interferes with the ability to objectively understand the physical reality of the world. And I think from there, it's really been the case that we've kind of thought of the mind as being this entity that's separate from the body and separate from the environments that it's embedded in. And I would add to that as well, because that's the traditional story. But I've always felt that there was kind of a sense of almost a self-centeredness in the way that we've understood everything scientifically, going back to the geocentric universe, where we put ourselves and human activity at the center of our understanding of everything. And since then, we've sort of been, I think, moving further and further away from this idea that human activity, or in this case, human consciousness, is something that exists outside of the rest of the physical stuff that we're used to being able to observe. And I think that the mind is kind of the one of the last dominoes to fall there. So I think the big difference between what can be considered a lot of things, computational approach, information processing approach, which today kind of still has that relic of dualism that exists, where we have to feel as if the mind is something that is unique physically, instead of thinking of it as a special case of ordinary physics, which I think the ecological approach gets us a lot closer to understanding the mind brain and all of psychology, generally speaking, as something that is subject to the same laws as the rest of the universe.
So can you give an example there? Somewhere where we had these dualist ideas, and then ecopsych comes in, and it gives us a different vantage point, or less human centric, or more embedded perspective on cognition.
I'm sorry, can you repeat the first part of the question?
Are there any good examples where ecopsych changed the vantage point of how we explained the behavior and how we studied it compared to previous representational, computational, information theoretical approaches? I mean, what kind of it has to have some wins, right? In the whole battlefield of science. So can you describe some of those wins?
Yeah, I think one of my favorite examples to use is distance perception. So before the ecological approach, and also contemporarily with the ecological approach, distance perception is described by what's generally considered Q theory. It's the idea that we need, because there's no processing in the retina there's no three-dimensional processing that takes place inside the retina. So the idea is that there has to be all of these hints from the environment that we have to use in order to judge the distances of objects from us. And the crux of that argument is one that depends more so on just treating the organ for vision as being singular and kind of divorced from the rest of the body. So it's the idea that the retina is the only thing that can be involved with being able to perceive distance. So then you end up with this quandary, sort of, where you have to suggest that people can't directly perceive distance, but instead they have to rely on these cues for it. And that really just all of those complications and weirdness that comes about from separating our sense of vision from the rest of our body can be completely washed away by considering that our eyes are in our head, and there's a distance from the ground in our eyes that all allow us to be able to really easily perceive things, perceive distance directly based on whether it's the horizon effect, or whether it's being able to create optic flow, which can allow us to perceive distances and even be able to alter our distance between objects in a way that is reversible. It all becomes far more tractable, and the explanations are clearer and more straightforward, I think.
I myself have this crisis, a lot of times when I read ecopsych and, practice ecological approach. One can always argue that what we do, generally speaking, we definitely reduce the cognitive load. So let's say we come up with these variables like tau, which are much more comprehensive about the embedding of the organism in the environment. They can reduce the problem of control, but it might be that computation might still be acting on that variable. So that's not a proof, like whatever we do and we have done in the core program is not a proof of non-representationalism, but is actually is reducing computational load. It's like when we write a code, we can make it more efficient, right? It's some of that kind of understanding of that algorithm or how brain might be implementing. I'm playing devil's advocate here. Okay, so it might be that rather than actually deciphering something about how the brain functions.
Yeah, I completely agree. It doesn't rule out other explanations, and I don't think that any scientific theory ever does. It could be the case that there are representations that exist, but given the fact that our starting point was to compare the mind to an object that was invented by humans, the idea that we think about the mind as this sort of digital processing device, that idea, it created a really weird starting place for our explanations of things that led, I think, to us thinking about things in a way that make representation the starting points of the theory, where I think that if we start at a different place that's more grounded in what we know about biology and physics, then we probably don't need that concept per se. That's not to rule it out or suggest that computations don't happen or that the brain isn't in some way a computing device. It's just, I don't think that we're doing ourselves any favors by adding explanations that don't necessarily explain things further than other better explanations do.
We had Jeff Fagban and Julia Blau on one of the previous episodes, and they kind of agreed that we can have representations, but it's not the way the brain functions. It doesn't operate on representations. It can have representations at a much higher level, of course, but does not compute the sort of representational information theoretical way. So
I agree with that, and it also just depends on what you mean by representation as well. If you want to talk about the way that information is processed in, say, like a star, for instance. The reason why we can trace back the events that have taken place in the distant past when we're viewing things astronomically is because when a star turns into a supernova, which creates a giant gas cloud or nebula, we can measure the elements in the nebula and know what was inside of the star. So in that sense, that is like information being preserved by the star that allows us to be able to understand its properties. And that's an example of information that might make a little bit more sense in terms of the way that we might describe the brain, is the idea that there's ways that you can kind of understand its history by looking at the different properties of its neurons, but it doesn't necessarily mean that it's actively processing
that's a
the
beautiful point.
information.
That's a beautiful point. Yes, that's a beautiful point, and I think that's kind of rooted in how we analyze data, right? What kind of statistics we do, what kind of correlations we find, right? Ultimately, we are trying to just find proxies, and that definitely that don't say that's not definitive about that representation happening and that computation happening. They might just be residuals of the history, as you said.
I think so, and I think that sometimes we get a little confused about what we mean by information, like the stuff that we're using to understand the universe seems to be being confused with the stuff of the universe itself in some ways in a computational approach.
Right. Luis Favela, he was talking about this, in much greater detail. We often confuse the things with how we what we do about those things. Yeah. So, Brandon, you mentioned, I remember your talk in 2015, you mentioned about planar polarimeter, right? As a beautiful analogy or a metaphor of how brain might be doing things. So could you elaborate on that a little bit?
Yeah, and that's an analogy I can't take credit for. So that's what is the scientist's name? I'll look it up later at some
Yeah,
point. It's, but yeah, that was written in the paper that I was referring to. Runison is his name. Yes, it was a I think 1977 Runison paper, and he compared the mind, instead of being like a serial processing device, which is what the contemporary explanation was, to a polar planimeter instead, which the polar planimeter is an interesting object because it's a tool that's used to be able to measure surface area directly. So it's used. It was used a lot by sailors in order to figure out where they were in the ocean, and all sorts of other uses in that way. And normally, when you actually measure surface area, you have to calculate it, and there's a
yeah,
number of different ways to calculate it that depend on the shape of the surface. And a computational serial processing perspective would suggest that you have to measure those things separately and then calculate the surface area. But the polar planimeter is, based on the way that it moves, able to directly not calculate, but measure the surface area itself in a sort of a clever way. And the idea is that might be a better explanation for what's going on inside of the mind than the idea that we're calculating the
yeah.
properties that we're able to perceive.
What struck me about that was, so let's take a square of side length L, and the area of the square is L square, right? So we are doing computation L square, but you also need to represent, because L square is a representation of a square. Likewise, pi r square is not just calculation of the area of the circle, it's also a representation of the circle, right?
Right.
But at the same time, if you have an extremely irregular figure like a moving amoeba, a planar polarimeter can still calculate the area of that. But if you ask us, manually calculate the area, what is the length? What's the width? What's the radius? We do not have any of those dimensions. So we don't have ways to represent, right?
Yeah.
So as soon as you go to these representational calculations, you first need to have representations, only then you can compute something. But how to make those representations in a world which is extremely uncertain, which is extremely irregular, and has these undefined boundaries. But none of that is a constraint with polar planimeter in calculating those areas.
Yeah, that's right. It's an interesting point too, that you're imposing a representation of a perfect geometric object in order to calculate surface area in a way that already is kind of divorced from the real world. And so this does sidestep all of the even representation that you need in order to calculate the new representation. And there's also questions about how that representation would have entered the system in the first place, which is another huge issue with the computational approach is the loans on intelligence, of
Must
course.
say, according to some people, we are born with those.
Yeah, what'd you say?
According to some, we are born with those representations,
Yeah.
right?
Right.
Basic representations, like a basic set.
Yeah, there's that starter set of
The
representations, I
starter set of
suppose.
representations, yes. Some are born with more with a larger starter set, than the other. So perception is more varied and more nuanced, right?
Yeah, right. It's all genetic, yeah.
Yeah, exactly. And this also, makes me wonder about a little bit about hallucinations and, the effect which, for example, LSD does, to your perception. I mean, are there any ecological approaches to what happens to vision during hallucinations and phenomena like that? Are you aware of
It's
any?
a it's a really good question. I'm not aware of any per se. I mean, I can talk about different explanations of illusions. Then there could be a theory or explanation that's similar to that. So that's actually
Okay,
how I.
let me ask you this. Like, what is an illusion? What's an optical illusion?
An optical illusion is when you take advantage of the basically the inability of an individual's sensory system to perceive exactly what's in reality. So you're perceiving something that is real in the way of an ecological description of an illusion, but it isn't what you are intending to perceive, or it is something that is kind of on the margin of some sort of process that exists for being able to perceive it, like for instance when you see illusory edges, but it is a very special case where you can momentarily or with the right conditions in a way make someone perceive something that isn't what they're intending to perceive, or isn't what they're supposed to be perceiving per se. Actually, the discussion of illusions is the reason why I got into ecological psychology in the first place.
How did it
I,
happen? Can you
yeah, so
recall? Yeah.
yeah, I went to I went to um, Illinois State University for my master's program because I didn't get into Colorado State, which is where I wanted to go because they had a big memory program there, which is something I was super into. So I went to Illinois State to study with Dawn McBride, who's Jeff Wagman's wife. And she's a memory researcher, so that's what my early research was memory research. And since I was in a master's program, I decided I'd talk to some of the other faculty there and see if I, really liked any of their research or maybe wanted to pursue something different. And I remember thinking that Jeff's work was really cool. And I remember in my first meeting with him about it, he was like, illusions are not real. And I was like, that's the coolest thing I've ever heard.
Yeah.
And I just felt like it all felt really natural to me. The explanations from the ecological approach. It also felt a lot more conservative as well. There's seemingly a lot fewer assumptions in most of the explanations. So it really just felt like the right way to go about things. And so that's how I ended up studying ecological psychology. But that's what he first used the example of putting a stick in the water,
Yeah.
and you think it appears bent. But of course, nobody actually thinks that the stick is bent. So you can just pull it out and perceive it in a way that allows you to actually see the properties outside of the water. But it's like you're very much aware, and you can interact with your environment in a way that you're never actually fooled by the illusion. Like it's not something that ever really seems to fool people per se, because of our ability to interact with the world and how that's a part of our perception. So yeah, those were the reasons I really kind of thought ecological psychology was an interesting and useful explanation in the first place.
What is interesting is regarding illusions that a lot of times we attribute them to representations, right? Like this is what we construct. However, when things change, the brain still has kind of stuck on that representation, and that's why we feel these illusions. I discovered some papers from 1960s, which are not even in online. Some of them are just in print. And there were experiments people did with pupil fluctuations with some kind of illusions. When you stop pupil fluctuations by giving some kind of drugs, suddenly the illusion disappears. So it's not in the brain, but actually your vibrations happening in your pupil, which are actually causing those sort of illusory effects.
That's
So,
interesting.
so I talked to Louis Favela, and we planned some experiments. We haven't gone that far yet, but the idea was that we will actually do some experiments and see how bodily fluctuations influence, given that a lot of these illusions are related with optic flow.
Mm. Yeah, that's really interesting, and I know that I've had the thought at times. in the study of body image, for instance, which the idea there is that people have some sort of internal representation of the way their body looks that may be bigger or smaller than it actually is, or they could be altered in a lot of different ways. And I've always thought it would be really interesting, and I don't know if anybody's done this, but it would be really interesting to see where people are looking. I
Yeah.
imagine that people look at their body differently if they, for instance, have body dysmorphia as compared to someone
Yeah.
who doesn't. And I think that might be a simpler explanation than people actually having a stored representation of their
Oh,
body.
it happened to me. So I was born in India, right? An average Indian is a few inches shorter than the people in US, as well as an average Indian is much less obese than people in the US. Average body mass is much lower in India as well. So when I landed in Atlanta for the first time, everything was huge. The airport was huge. Okay, all the installations were huge. People were
Mhm.
huge working at the airport. And when I came out and I was in the van going to University of Georgia, on the way, the warehouses were much bigger. Like everything was huge except myself, right? And I remember like for several days and weeks, I felt a little small in size
Yeah.
because things were different. And that made me wonder what happens to people who are shorter in generally, especially from for example, one gender, like women have average lesser height than men. So I always then started wondering like how much your perception of these bodily dimensions affect your behavior and affect your situatedness, as well as how it changes when you go into a different population or different embedding.
Yeah. It's welcome to America.
Yeah.
It's it's a really great question, and I imagine it's pretty similar to like when you walk on a moving walkway and step off of it, you kind of have that recalibration effect that can take place there. It might be something similar to that.
Yeah, but it again it does not defy representations, right? Like one can still argue that you are recalibrating your representations as if just like you have these images clip arts in PowerPoint where you can have your clip art and you can just extend the size a little bit just by pulling out the boundaries. Similarly, you can have those representations in the brain and somehow you can recalibrate by increasing the gain or the loss of a neural drive.
Yeah, that's that would be a computational explanation of it, which I believe was what
It,
the
it
original explanation was with I think that's the riser studies where they had like a tractor pulling a a treadmill, and they tested all these different ways that people recalibrate. I believe they had originally a computational explanation for that. But yeah, with recalibration, that's not really necessary. It's if you think about something that's changing over time, then all you're doing is just recalibrating your perception with your action. So when you're on the moving walkway, the relationship between the movement of your feet and the optic flow that you generate is disrupted. And so you get used to that new way of interacting with the world, and then when the conditions change, then you also recalibrate back. Or it's also similar to the way that we calibrate to prism goggles. It's another good
yeah.
example of that, where at first you can't really throw an object straight to someone if it's shifted 30 degrees to the right, but then after doing it several times you can start to do it. It's like your relationship with your environment has changed, and we just really quickly adapt to those changes. And the more difference there is between the initial conditions and the current conditions, the more of a sort of disjointed calibration effect I think it produces right off the bat.
Right. So yeah, so we do calibrate and we do it eventually. It does not happen in one go for most of the times, especially the sensory motor discordance. Uh, yeah, but why do you think? I mean, most of the explanations are still computational for that particular phenomena, right?
Yeah, the existing explanation of the
Yeah,
well well there is a computational explanation of it, but probably the most well developed explanation of it is comes from a lot of Brett Fajan's work, where he's looked at how people recalibrate to changes in brake effectiveness or brake strength, excuse me, and in that case, people can recalibrate in a single trial
yeah,
to changes in the brake strength, but it just seems like a coordination issue in the way that it's explained from that perspective, rather than one that necessitates some sort of process in the nervous system per se.
I see. So basically, that reduces this whole idea of having internal models because you don't need internal models explicitly for each of these tasks. Just the neural tuning for calibration can take care of all these varied kind of perturbations, right?
Yeah, yeah, I think so far it's explains most of the stuff that we see in those types of recalibration experiments. And similarly, you have the attunement work as well that's been done by a lot of people, including Eleanor Gibson and Claire Michaels, and her theory of direct learning, which is a really interesting way to describe how we're able to educate our attention, if you will, and be able to detect the information variables that we need in order to accomplish a task. So those were all really fascinating things for me because I've always been so interested in memory and change over time. So those are all really, I think, powerful
Yeah.
theories and useful ones, yeah,
No, so
that deal with some of the representation hungry types of phenomena like learning.
so I exactly wanted to discuss that with you. So you said memory, and whenever I discuss ecological psychology with some of my computational friends, uh, uh, I mean friends who endorse computational theories, they always come up with these representational hungry problems. And one of their complaint is that we ecological psychologists generally stay away from representational hungry problems, and we are able to get away with it. Uh,
Yeah.
so you said memory. Like, so what do you think about like how does memory fit in the ecological framework, and how do we explain memories and things which probably need memories, like dreams?
Yeah, this has been something I've been interested in and working on my whole career, and it started with a conversation with Jeff in a bar when I was in my master's program, as most great ideas do. And basically, I just asked him whether or not you could turn an affordance task into a memory task. And then we were like, yeah, I don't see why not. So we did that first study, just seeing basically, what's happened to people's reports about affordances when they had to remember them, and we've ended up through a lot of different studies finding that there isn't a whole lot of difference between memory and perception, at least in terms of affordance perception. That people's memory for affordances is really similar to their perception of affordances, and so I've just been trying to come up with some sort of theoretical explanation that is able to distinguish when something becomes a memory and when something is perceived. And that's something that we just kind of blew past in psychology, is any sort of actual accounting for the way that perception and memory are demarcated from each other. It's something that is different depending on when you're reading it, and there's sort of a common sense assumption that's used about when perception ends and memory starts. And some people think that everything is memory. So even when you're perceiving things, you're always using even if it's just slightly past events, so you're using past events in order to perceive it. And other people think that perception is an extended phenomena, but that it ends at some point, and then memory begins. I've been spending the last several years reading about a lot of physical theories of time, if the one that we sort of assume is the basic, general relativity description of time, which suggests that very few things have uh, a um, a space-like interval, which means that they're interacting simultaneously, and there's just space that differentiates the two events. That's something that's exceedingly rare, and most things are time-like. There's some sort of distance in between one event and another event in time, and that's the same thing for all of us. Gibson described this in a paper in, I think, the 60s, I want to say, as a razor's edge of time. So the idea that the moment is always fleeting, sort of like being on
Yeah.
this Zoom. If you look at the time right now, then you can't look back at yourself looking at yourself. Like it's similar to that. That seems like a really poor description of what
Yeah.
our experience of time actually is. We do experience a present. The thing that occurred to me that seems to be what actually determines what the present is all of the things that we could potentially do. So all the actions that are afforded to us at any given time, because what ends up happening in the past, once an event passes you by, is we as living things can no longer interact with those events.
Yeah.
Even if you go back to a place that you'd been 10 years ago, that you're not in the same space-time location ever again, even if you're in the same spatial location again. I think really the thing that actually should define the present is our ability to interact with our environment. That seems to be something that's limited, and something organisms have adapted the ability to do is live at that front end of an expanding timeline, or what's known as a world line. And be able to affect the events within that window of time. And I think that's a better explanation of the present.
This issue is so complex. So, when you read introductory psychology textbooks, cognitive psychology textbooks, you have the short-term memory, and then you have this medium-term memory, this long-term memory, and somehow short-term memory is transported to some, medium-term or long-term memory areas, right? It's called consolidation, right?
Mm.
And then when you actually look at the phenomenology of perception and action. So while I'm reading a book, I read, if I'm reading a page in 40 to 50 seconds, almost a page, right, on a regular basis, that's a lot of words. There's not even if you look at the transmission time from vision to the area V5, and then whole processing, you don't have that much of time to be able to assimilate this kind of information, right?
Yeah.
That cannot happen in real time. And then if that happens, that's a lot of information. Converting that, that visual information into the meaning of those letters and the syntax, and then transporting that, a consolidation of that from one part of the brain to the other, as if the whole copy is being represented, right? Because when we do things in computer, for example, when I move a file from one folder to the other folder, it does not physically move the information in the memory drive from one part to the other. It just changes the label of that, but the information remains the same place, right?
Yeah.
When we think about the brain, suddenly we think about this transportation. So even the ideas of memory in the brain, the computation ideas are not actually uh, purely aligned with the computational, like the real computational view. It seems like a made-up fiction
Yeah.
in multiple ways.
Yeah, I agree. And there was who's I'm bad with names here today, but yeah,
Yeah.
there was the neuroscientist, I believe. Oh, it's Carl Lashley is who it is, I think, who was spent his whole career looking for the memory engram and could never find a location in the brain that seems to be specific to any particular memory
Yeah.
in his work, and we've just as a field kind of papered over that. I mean, that's sort of
Right.
a huge issue, one that doesn't really have, I don't think, a tractable solution to. I think that the way that some people have kind of rethought of memory from a computational perspective is in terms of the overall system activity of the brain, or the activity in certain regions of the brain, maybe being responsible for storing memories and their patterns of activity. But yeah, the way that we think about memory from a computational perspective is flawed in a lot of ways, and we sort of should have known better. But I think the computational approach has been so productive in so many ways that it makes us easy to kind of ignore some of those fundamental issues with it.
Right. I mean, on that note, I'll describe you this incident that happened to my father. So my father was diagnosed with fourth-stage cancer. So he had renal cell carcinoma in his right kidney was cancerous, and he had a metastasis in his left frontal cortex. So while he was getting his nephrectomy, he went into coma, right? And he was almost forgetting everything. And one of the surgeons, a neurosurgeon, prescribed him the surgery to remove the tumor from frontal cortex. Of course, he couldn't remember anything. He couldn't identify me as his son. He couldn't put his signature on paper, things like that. But we were skeptical because he had comorbidities and it was like a risky operation. So we went for second and third opinion. And there was this neuroscientist, more like a physician, and he suggested that it might not be the tumor. Just because there's a tumor, we are attributing the cause to that tumor. What if there's something else? So he ran a whole battery of physiological tests. Nothing came out. Then finally, they did a blood ammonia test. Generally speaking, ammonia levels are not high. What they found was that even though his liver scans were clear, liver was functioning well, he had this buildup of ammonia in his blood. And because of that, there was toxicity happening in the brain. So they removed the blood ammonia using a drug. And within a few days, his memory was back gradually. So something which is a metabolite in your blood, right, is restricting your memory despite your wherever the memory is. Let's say if it is there somewhere, it was intact because everything came back. So it was like the memory was there somewhere, and there was a cap on that bottle which the ammonia had put, and as soon as you remove the ammonia, the cap was removed, right? And suddenly now by the idea of causation, or how relationships interpretation of statistical relationships work, one might say that memory is basically a metabolic phenomena, then actually have some spatial temporal property to it.
Yeah. First of all, I'm sorry to hear about your dad. That sounds really hard.
Yeah, he's
Um,
doing good, but now, yeah,
that's good to hear. Good to
yeah,
hear. It's, Yeah. Also, yeah, it's that's a really interesting example because it was seemingly just affecting, what would be described as the retrieval of those memories rather
yeah,
than affecting their existence, or making them like them being omitted from the brain
right.
completely. So, yeah, it seems as if some process was being disrupted rather than like some of the storage system being removed.
But
If
how can we ever be sure with any experimental design that whether the storage system is removed or whether it's a retrieval which is compromised?
Yeah, it's difficult. I think, I mean, with your dad, it sounds like that's a pretty clear example of a case where it's hard to argue that you can't really explain it in terms of there being the actual memory traces themselves being disrupted in any particular way. It just seems like they were locked away and the access to them wasn't available anymore, while he had those toxins in his nervous
Yeah,
system. So that's one case study example, I think, of a way of parsing out those possibilities. But yeah, this kind of gets back to one of the biggest debates in memory's history, which is about forgetting. So, do we forget memories because of decay? Do they decay away and disappear in the nervous system, or is it an interference phenomena where the way I like to describe it is that if you have a giant room full of files, if you file something in the wrong place, you might not be able to find it, but it's still there. That's basically what interference theory suggests. And this case with your father, it sounds like it'd be something in the positive side for interference theory, the idea that we never forget anything, we just lose the ability to be able to access it. But I don't think it's necessary at all to invoke the nervous system when describing how we experience memories. I think one of the things that we've learned in physics is that you can't separate space and time from each other. They're inextricable, and changes in space influence time and vice versa. This, I think, suggests that what might actually be happening is that we might, like the universe is, be expanding in space time ourselves as we go through our lives. And it's not necessary to suggest that we have to remember things that have happened to us in the past. There are things that have happened to us, and they in some ways continue to exist because we're aware of them. So we're able to know them at some point. So it's not like we have to necessarily look through our nervous system to find memories, but instead we have to just look through time the same way that we look through space, essentially, is what's happening. It's just that things become more interferable with each other, like they can interfere more and more with each other as time goes forward, because they become events that are all stacked on top of each other. I think you could explain memory, and I've attempted to explain memory in this way, where the big difference between remembering something and perceiving something is perceiving something means you can interact with it, and remembering something means that you can't interact with it anymore. I think that might account for why the experiences are different from each other, and why we experience a
Yeah.
presence and a past.
And you cannot interact with that anymore. Okay. So is this just a definitional reconstruction, or like how does it change how we go ahead with the enterprise of neuroscience and psychology? Uh,
Well, it is a huge theoretical difference in the sense that it changes the way that we think about the mind's role in remembering things. So in this case, rather than suggesting that we've perceived something and then stored it, and it's being used to perceive things in the future, which comes with a lot of assumptions. The explanation is instead that we perceive something, we continue to be aware of that thing that we perceive because we're expanding through time. Just because we can't reverse time the same way that we can space, means that we have a different relationship with the temporality of events than we do the spatial nature of events. But otherwise, it means that you're not going to find anything about memory inside of the nervous system per se. It's all just in the record of our being conscious beings that were aware of their environments and continue to be aware of those things. So it does have some different predictions that it would have. One of the things that I'm excited to start testing, hopefully this semester, is whether or not memories are time dilated. If you look, now that so many telescopes exist where they can look back at the early universe, there's been a recent study where they found that the speed of light was actually 5 times slower in the early universe. Like a really early universe, which may seem crazy because light is supposed to be a constant, but it's consistent with general relativity theory because the space itself was smaller. It was the case that for that reference frame, the speed of light is slower compared to our speed of light now. So time dilation happens at pretty small time windows. So it should be the case that events that are in not so far past should be ones that's become dilated. So that means that when we're remembering something that happened yesterday, it should feel slower than if we're remembering something from 5 minutes ago. So this would be a way of testing whether or not we're recalling the events in our
I
nervous system, because those wouldn't be time dilated because
Yes.
it's sort of like watching a video. It'd be like, it doesn't matter how old the movie is you're watching, it's not going to be time dilated because you're watching it in the present,
Yeah.
which it was carried forward through time. But in
Right.
events, if we're experiencing it and it is just something that's actually in the past that we're experiencing time dilation should be directly related to the interval between the present and those events. So that's something that I haven't
I would
figured out
agree with
exactly.
you. I would agree with you here because, and this is something, by the way, I never thought in terms of theory, but I thought in terms of experience. Just of my schooling, history of schooling and college, right? So when I go back and you ask me, like, how was your class 8? How was your class 5th? The earlier I go back, the slower time seems to be. The more activity I think happened in those, when I recall, not necessarily in those time spans. So I see this when I actually think about my past.
Yeah. I have a similar sort of common sense experience with time where it does seem slower the further back it is, and I think that it'd be really interesting to find that effect because I think it kind of rules out the computational explanation of memory because you can't be
Yes,
if you're remembering something, then there's no way that it should be time dilated. We know that by watching any old movie that it's not. So yeah, that's something that I think is consistent with the ecological approach and
it is.
is one that doesn't necessitate the use of
Although I
notice.
would say that there might be some computational theorists who might come up with an explanation of some kind of physiological degradation which might cause that even in a computational system. So be open to that possibility.
Oh yeah, there's always a way.
There's always a way to resurrect computation.
Right. You could make just about anything into a communication device.
Yeah, of course. I feel that it's a. I don't think it's a falsifiable hypothesis.
Yeah, that's definitely an issue with it. It's true. There are very few ways to rule it out, which makes it less useful as a scientific theory for sure.
It's more an axiom than a theory.
Hmm. Yeah, and it's just not usually a. I mean, it also just it stems from I don't know why we feel the need to compare ourselves to a device. It doesn't it doesn't seem like a good starting place because we built the device and the things that we build don't tend to be a lot like the things that exist in reality otherwise. It I think is flawed in that sense too, but it also makes a lot of sense just because it's something that allows us to take something that's really difficult and complex and hard to understand and
Yeah.
give it turn it into a device that we understand very well and we can pull apart and see how all the parts fit back together with each other. And so I think from that perspective, it's really useful, but it's also just, I think, not the right place to look for a theory about a natural science theory or a life science theory.
You know, I took a class for dissection, anatomical dissection of the human body. It was not supposed to be for psychology graduate students, but I took a special permission to do it in the medical school with medical school students. Uh, and I think almost all of us should try at some point if we can somehow be a part of a cadaver, a human cadaver dissection team. And even though you're working on a cadaver, once you open it, no matter which part you're talking about it, your respect for surgeons who not just open it but put it back together just
Yes.
increases, because it's
Sure.
so hard to put it back together. It's extremely hard. It's so
Yeah.
packed. It's so efficient. I mean, there's not even like a single bubble inside the body. There's no space, which
Mhm.
is wasted, right? And as soon as you cut open, air goes in. It just changes the whole thing.
Yeah, yeah, I think that's a really interesting point. Yeah, trying to put a cadaver back together again isn't something that seems particularly possible, even though the computational assumptions would maybe suggest that it is possible. It kind of
Yes,
reminds me of the kind of brain in a vat type of thought experiments. Yeah, where you can just interchange parts with each other for humans, but I don't think that there's very many things naturally that work that way. Most things, once you take them apart naturally, especially because of the laws of thermodynamics, they can't really go back to what they were
right,
before.
right. And then even the parts which we actually implant, for example, or tissue, they're the ones which are the most isotropic tissues. So if you look at our success with transplantation and our success with regeneration of body parts, the more isotropic it is, the more successful we are. And when you look at the brain or the nervous tissue, it's extremely anisotropic.
Mhm. That's really interesting. Yeah, yeah, that makes sense. And yeah, the other thing too is that it's also the case that that the nervous system is made up of a lot more than just the cells that we're attributing some of these things to. So
Yes.
neurons aren't even the most abundant cells in the brain. So it is the case as well that there's a lot of assumptions that are being made about that, and maybe if you know decompose the glial cells, you'll see something that you're surprised to
Yes.
find.
I always wonder that, what if we did not have electricity? We had some kind of chemical methods to chemically look at brain. In that case, our theories of the brain would have been completely different. Just because we could start recording from the neurons, as well as we could look at the magnetic fields produced by the brain. Uh, we had these kind of interpretations.
Yeah, yeah, those are all really interesting possibilities for sure. And yeah, and the other thing I always think of with this conversation too is just I do this with my students. In fact, is I have them do a thought experiment where they have to build a machine that works like that perceives the world the way that we do. And it sort of highlights how weird all of our organs are and that they don't work in ways that you would ever design. That's the way that light has to pass through the retina before it reflects off of the back of your eye and gets picked up by the retina itself is just, it's something that an engineer would probably have a panic attack over. So,
In that case, my favorite example would be to have genitals which you use both for excretion and both for procreation, as well
yeah,
as
right.
procreation, right? I mean, who would come up with that weird design? That's the weirdest thing to think of, right? I mean, if you are a designer in the the whatever the factory where humans are made, and you come up with this idea, you'd be fired instantly.
Right, exactly.
Yeah,
That's a great way to get fired. Yeah.
yeah. So yeah, definitely, that's the case with almost a lot of body parts. Yeah, I mean, with the eyes, the structure of the eyes, one of the classic ones.
Yeah, yeah, and then the auditory organs are all really strange too. They have to convert energy into through different mediums in order to get through
Yes.
to your nervous system.
And
So
you can grow your skin and you can grow your muscles, but can't grow your teeth. If I would have been designing, where most of my pleasure comes out of chewing and my existence comes out of chewing, I would like to have like 10 pairs of teeth over my lifetime.
right, exactly. That would be nice. It's true.
right?
Just grow some new ones, take the
Yeah,
old ones out.
there won't be any Freudian dreams of shedding your teeth.
Right.
Right. Brandon, you mentioned teaching. So let's talk a little bit about your teaching. I didn't know that you were transitioning to teaching when I met you. So how has your experience been with uh, as an instructor? And we have very few instructors who come from the ecopsych tradition and imparting these new ecopsych wisdom to new generation of students.
Yeah, it's always been a little difficult because I've taught perception since I was a grad student, and the way that in my experience, at least at the University of Cincinnati, and I think that Jeff teaches it this way too, is to cover the whole class as if it's from an information processing perspective. So it doesn't, we don't have at least not until recently, until Jeff and Julia wrote that textbook recently. There hasn't been, an ecological psychology textbook. There also hasn't, you mentioned earlier how we've mostly stuck to perception action because we don't have a whole lot of folks that are doing this research, even though I'm always very impressed with the production of ecological psychologists, relatively speaking. But we don't have like the widest of breadth of topics necessarily, even though we're starting to get closer to that. So usually what I do is have a single unit where I discuss ecological psychology, and I discuss it within the unit of perception and action, which is something that is really commonly in textbooks. So they can also read about that. And we talk about the ecological approach from a pretty broad perspective, mostly just talking about affordances. I usually have them come up with pi numbers for some affordance that they have to think of themselves, and we also cover some of the action specific literature as well, which is kind of the ego light version, I think, but
I mean,
also very interesting
we
and
we have
important.
Michael Turby's lectures in perception and the action coming out soon. Although it's a little higher level, it's more like a grad school level book, but that's also a beautiful resource.
Yeah, and it's students. They usually are and I wouldn't expect them to have any other impression of it after we spend the whole semester talking about things from a computational perspective. But they
Yeah.
just they struggle a little bit with the ideas, but they end up getting it. It's always been weird to me because we have to use pretty sophisticated scientific tools that a lot of our colleagues don't use, or they use different sophisticated tools. But I feel that the explanations themselves, even though they might be they might involve having to talk about the inertia tensor, for instance. They also are usually pretty straightforward. So like
Yeah.
the outfielder problem is one that I'd love to use as an example a lot too, because you think about catching a fly ball as being this really complicated perception action process, and really all you have to do is just move so the ball stays on a flatter trajectory, and you'll end up being where it's at. It's really simple explanations that involve complicated science, I think.
Right. But isn't it challenging that the students are taking some, probably you're not teaching all the courses, right? Like a lot of their courses are very orthodox cognitivist, and then suddenly you are teaching them something which is very different than what they have learned in some other classes.
Yeah, it's definitely, and I'm the only person who even does we have one other person who does perceptual research, but I'm the only perception person here. And everyone else is more from a cognitive area, and we don't have a ton of cognitive psychologists. I think more than half of our faculty are and staff are clinical psychologists. But yeah, everyone obviously uses the information processing approach as kind of the meta theoretical background for what they teach. And yeah, we usually only cover that in a unit in perception. I don't talk about it in any other classes, but it's also the case that my students in my lab will also have a little bit of trouble understanding things at first, but they always get it pretty quickly though, given the fact that you have to completely change all of your assumptions,
It's also
like your
more
underlying
intuitive.
assumptions.
I
Yeah.
think it's more intuitive.
In a
See,
lot of ways it is.
yes, yeah, my analogy to is like the imperial unit system versus the metric system, where like an ounce feels weird to calculate, but at the same time, it's very intuitive. Like this is an ounce, or like a feet. A feet is like, okay, yeah, it's a little odd value compared to a meter, but at the same time, a feet is more intuitive than what a meter is to an individual, right? Or a mile, or any of those measurements. So it might feel difficult to begin with, but when you understand where it is coming from, it's much more intuitive and it remains with you compared to a metric system, which a lot of people have a hard time calculating and at least imagining.
Definitely. And I don't think the biggest barrier is learning the subject matter itself. It is more about just getting past some of those assumptions that people don't realize that they have. And that's I think the biggest barrier for us as a field. So I think it's one of the reasons why we've had trouble getting off of the fringe of psychology, is because there's just a lot of baggage that everyone has when it comes to the underlying assumptions that that's it's really hard to work through. I think it's also one of the reasons why so many terms from ecological psychology get kind of appropriated.
Yes.
Like the term affordance is very much been computationalized by a lot of researchers, and generally speaking that's a good thing. It should be the case that we should be trying to find ways that theories can accommodate for other theories, and that's an important part of science. I mean, if Einstein's theory of general relativity uh, couldn't explain Newton's mechanics or phenomena that Newton's mechanics explain, then it would be a problematic theory. So it is good to make those attempts, but I also think that it comes from a place of people not being fully ready to break down all of those underlying assumptions that exist.
Right. Right. Unfortunately, we can't have an affordance oversight committee, which kind of, you need a clearance from them to use the word.
Yeah. But yeah, I think I was listening to your podcast with you were talking about that.
Sure, yeah, yes. So, and when you said that about this indoctrination and how hard it is to get passed by, I sometimes feel, and I always quote Stalin on this. Stalin used to say, quantity has a quality of its own. And I think that's very much applicable to this point in time about ecopsych. We need to generate enough quantity of literature and enough quantity of resources, textbooks, uh, and content for people, because otherwise, statistically speaking, the visibility is too low.
Definitely. Yeah, it is. It is definitely something that will need a lot of people working at it in order to shift the tide a little bit. And yeah, I think I think ultimately we'll get there, at least maybe not necessarily adopting ecological psychology in the mainstream, but we'll get to a point where people finally tear down those sort of computationally based assumptions that they have. But history suggests that it might be a really long time because it was like
Yes.
1,500 years, something along those lines, that everyone was in agreement that the Earth was the center of the universe, even though if you look at the sky, it's pretty clear that it's not. I think we're probably in a similar situation with this, and hopefully the thing I'm hoping for is that there'll be some sort of enormous groundbreaking study. So I think that's sometimes the thing that can really speed up that process a lot. But I think without that, then you're right. Just having more people who are trained as ecological psychologists doing that type of work, and then training other people to do it will be another way that we start moving in that direction. I'm really encouraged by the way that the complex systems of approach has really, I think, connected us with a broader community of scientists outside of
Yes.
psychology. That is something that seems to have a lot of momentum.
Yeah.
And then the 4E cognition and body cognition stuff is obviously not consistent with ecological psychology, but it is moving in the direction where we're kind of on the other side of it. So I think I've been encouraged by those things for sure.
Right, and one of it has a more practical kind of influences. For example, time series analysis and how we look at network, how we look at coordination, and the other one is more meta-philosophical and meta-theoretical. Uh, uh, I see in approaches.
Definitely.
Yeah. So Thomas, Brandon, before we end the episode today, what are you looking forward to in the near future with your work in ecopsych? What are some of the directions you are moving in?
Yeah, so my main project right now is testing the the theory of time I suggested. It's not, I don't think, of like a full, it's more of a starting point for a theory than it is a comprehensive theory in any way. But I want to get further with it by testing certain aspects of it. I'm in the process of collecting data on one experiment for that, and then I want to do the time dilation study at some point this semester as well. So that's something that I'm looking forward to working on. And then otherwise, we've been doing some experiments using uh, like old psychophysics analytic frameworks. We recently published a study looking at trying to describe affordances from a power law framework, the same way that Stanley Smith Stevens did back in the 1950s, I want to say, 40s, 50s. And we're not trying to adopt the theoretical positions of psychophysics. Like there's no necessity to do that because it's not even a mainstream theory anymore. But we use a ton of psychophysical methods that were really powerful, and the analytic framework itself doesn't have theoretical assumptions. We found some really interesting things about reaching affordances by doing some experiments on the power law scaling of the perception of those affordances.
Nice. So you look forward to it.
Yeah, definitely. Should be fun. It's nice being past the pandemic and being able to collect data. Well, not past it, but yeah.
Well, I directed a lot of my efforts on simulation and statistics and statistical physics, so which helped me a lot during the pandemic, and it still continues.
Yeah, you get to sit in a room and calculate stuff. So.
Yes, with a number of monitors, on my workspace, it's kind of pleasure.
Yeah, that's cool.
So it was nice, Brendan, talking. I think we covered a lot of good grounds and a lot of thoughtful discussions. And I would definitely love to continue discussing with you some of these issues in greater detail. And hopefully you would love to come back again at BeyondPhrenology.
Yeah, of course, Medora, anytime. It's great to be on.
So good night, Brendan.
Good to see you. Take care.
Yeah, bye-bye.
Bye.